Pleasure to see all of you. I'm Vijay Kumar. I'm the Dean of the school. And it's my honor to welcome all of you to Penn Engineering's 31st Pender Award lecture. The first such lecture was in 1972. So this is a long tradition. And it's in fact the school's highest honor. It's presented to individuals in the engineering profession who have achieved exceptional distinction through significant contributions to society. Many of you know this. The award is named for Harold Pender, who was the first dean of Penn's Moore School of Electrical Engineering. In 1924, Harold Pender co-founded International Resistance Company, called IRC, which led to his developing and patenting the composite resistor in 1932. He was the dean of the Moore School at the time the ENIAC was developed and kicked off, I guess, between 1945 and 1947. The Pender Award recognizes individuals, as I said before, whose contributions made an impact on society, but particularly following on Dean Pender's tradition of innovation. Past recent recipients include Jan LeCun, Barbara Liskov, Robert Kahn, Vinton Cerf, and Mildred Dresselhaus, among many notable engineers. Unfortunately, I don't get the privilege of introducing our recent awardee. That pleasure goes to Tal Rabin, my colleague, who's a Radcliffe professor, family professor of computer information science, and she will introduce this year's winner.
So it is indeed a huge honor to introduce Shafi Goldwasser, who's an extremely prominent researcher, I'll tell you in a second, but also one of my biggest mentor who really sort of set my career. And I always had someone to look up to and to really admire and to show me what needs to be done and how you are and so on. So that's on a very, very personal note. Shafi, of course, I can say many, many things about her. She's currently the director of the Simons Institute. She's been a professor at Berkeley, at MIT, at Weizmann. Any department that she goes to turns to be the top department in the world just by her presence alone. She is, it's true, don't laugh. And she got her bachelor's from Carnegie Mellon and her PhD from Berkeley. She's a Turing Award winner. She got the Gödel Award twice. She's an RSA Award winner in math. She's a member of the National Academy, the American Academy of Arts and Sciences, the Russian Academy, the Israeli Academy, the Royal Academy, the Royal Society, and she's gotten many, many honorary degrees. I can keep on reading to you such awards that Shafi has gotten, and we'll never get to the talk. But the truth is that no matter how many such awards I will read to you that Shafi has gotten, they will fail to capture the amazing work that Shafi has done, because her work is magical and innovative and completely novel. And the thing is that every work presents a new idea. Not, okay, some works build on others and so on, but very often there is just a whole new idea, direction, and so on. And I can also describe many of these, but I want to give one example just so you get a flavor of the amazing things that come from this mind. So she, with Silvio Micali, they introduced the idea of zero-knowledge proofs. Zero-knowledge proofs, when they were introduced, nobody thought much of them. The paper barely could get into a conference. But of course, the ideas there were so unbelievable that today this is part of blockchain technology, of cryptographic technology, and many, many more places are using it. But what's sort of an unbelievable idea that exists in zero-knowledge proofs? Okay, first the idea itself that you want to prove to somebody a theorem without them learning anything beyond the truthfulness of the theorem. Yes or no? Okay. But now you introduce this unbelievable concept of zero knowledge. What would it mean that something would be zero knowledge? So in this unbelievable work, they came and they introduced the notion of a simulator. And think about, what does the simulator do? It says the simulator, as you can assume, it simulates a conversation. It will simulate the conversation as if a prover that knows the assertion would carry out that conversation, but that simulator would work without the knowledge that the prover is using. It only will know if the assertion is true or false. And this idea of a simulator, think of a coming out of it, out of the blue, in order to try to prove that something is zero knowledge. It has to be a mind that has, that reaches for the sky with its ideas. And this is really sort of the essence of what Shafi is. And you're honored, really, that she is here today to give you a talk, which I'm sure is going to be just as exciting and forward-looking as all of her research has been. Thank you.
So, wow. First of all, I'm really honored to receive the Pender Award, and I'm touched that I've been selected. And second of all, wow, Taz, thank you for your amazing words and friendship and kindness to describe me in such a way. And actually, I'm glad that you reminded me of the simulator paradigm, because maybe if I can remember till the end of the talk, I could talk about the simulation paradigm, maybe this machine learning space, which hasn't been utilized yet, but I think could be a useful paradigm to talk about what is the power of these systems. That this is not the subject of my talk, but sort of there's all of this revisiting of Turing definition of what it means to be intelligent right now with these new systems that we have out there. The definition always talks about indistinguishability. In cryptography, my mic is not on. In cryptography, we often talk about indistinguishability, and which is one definition, to say that two things look the same. So let's say a human and a machine, and you could query it and get back answers, and that you cannot tell them apart. But we also talk about the simulation paradigm, which is what you can do with one is that you could simulate what you could do with one with another. So you could imagine that definition replacing the Turing test, saying that whatever you could do with people, you could do with a machine, and maybe vice versa. And that is not necessarily equivalent to indistinguishability. So it's a stronger definition. It implies composition and many other things. But you remind me of simulation, so I think that paradigm actually is an interesting paradigm to talk about what you can use the AI systems for, rather than necessarily whether they look or don't look like human, which is the current thing that captures everybody's attention. It's like, wow, it looks like a person sitting in there and answering. But is that really the crux of it? It's unclear. Okay, my talk today. So the title of my talk today is Constructing and Deconstructing Trust. And the picture here is a picture of the Simons Institute, of which I am the director. And let me explain the title. So I'm a cryptographer, really, by training, and most of my research has been in cryptography with excursions to complexity theory, randomized algorithms, and so forth. But if we think about cryptography, there's a lot of tools. Usually people think about encryption, authentication, maybe zero-knowledge protocols, program obfuscation, public ledgers, blockchains, and so forth. So you can think of it as a bunch of tools, but more than that, there's sort of a unifying theme, which is, one way to think about this is that it's how we can use technology, which we assume is controlled by an adversary, or at least there's an adversary lurking around, and yet we can use this technology assuming as if there is no adversary. So if you think about it, it's a way we enable you to trust technology even when there's an adversary present. So in terms of encryption, if there was no adversary listening on the line, we don't need encryption. But we're saying even though there's someone listening on the line, I'll be able to communicate privately with someone. In case of authentication, I want to prove my identity because I'm afraid that other people are trying to pretend to be me. In program obfuscation, I want to run my program maybe in the cloud, but I'm afraid someone is looking and wants to learn my algorithm, so I'd like to obfuscate my program so So I can run it in the cloud without somebody learning the internals. But if there is no adversary, then there's no reason for cryptography. So cryptography always really, if you think about it, always is a way to enable you to trust this fantastic technology that we've come up with, even though you know that there might be adversaries. So from this point of view, we have this sort of recipe that this type of approach has been since the mid-70s. So we kind of know what we're doing. I mean, we do know what we're doing. So often it is, what is the task that you want to do, whether it's communicate privately or access a database in presence of somebody who's trying to gain access and pretending to be you, program obfuscation, and so forth. And then we say, okay, who is the adversary? Let's model the adversary in some precise theoretical way. Let's define how good a solution we want. So if it's encryption, maybe it hides all partial information. If it's authentication, you could have some other model of what it means for a solution to be secure. And then you build a primitive. And what's very important about a theory-grounded cryptography is that you show some sort of proof. And the proof would look like this, that if the adversary that you define will violate the security that you define of the solution, then either you show that it's impossible to violate it, or you'll show that if it does violate it, then some assumption is violated. Okay, so often we're making assumptions. What are the assumptions are? The assumptions might be the kind of assumptions you're familiar with, like that some hard problem in mathematics all of a sudden becomes easy, like factoring integers or solving some geometric problem or on integer lattices. Could be other problems. Some favorite difficult problem that we believe takes, let's say, exponential amount of time. And if an adversary exists that violates your security of the solution, then all of a sudden you have a solution for the problem in polynomial time. This is not the only assumptions we make. We make also assumptions, not everyone colludes. So this is if there's many people in the system, and you might give a solution saying, as long as, let's say, less than 50% of them are enemies that collude together against the rest, the solution is secure. Another type of assumption we might make is that you have perfect channels between pairs of people, where there's absolutely no information leakage, and if you have every pair of people have a perfect channel, then the whole solution works as a whole. Or you might make some assumption about secure hardware. You might assume very precisely how secure the hardware is, and then prove that your solution rests on this secure hardware. Okay, so the thing is that the adversary is key both for why we want cryptography and also for how what is the quality of the solution. So it could be good for one adversary, but not good for another adversary. So it would be good for a polynomial time adversary, but not good for an exponential time adversary. All right, so, and again, if you think about this from the trust perspective, it sort of tells you a recipe whether you should trust a solution and also whether you should not trust the solution. So sometimes you may be able to prove that no matter what solution you give, it's going to fail. So when distrust is warranted, there's an impossibility of a definition to be achieved. So no matter what solution we come up with, it will be impossible to achieve because you have set your goals too high, your definition of security is too high, your adversary is very strong, and so forth. So why do I want to talk about cryptography in terms of trust? Because this is really the topic that I'm interested in the context of this talk. And we know that in the last, 2 decades, people are talking about trust all over the place. They've talked about replication in science crisis, right? That seems to be hard to replicate scientific experiments in psychology, in biology, and should you trust the experiment or not? And can you do something short of running it again and again and getting similar, statistically at least, results? Then around 2016, around the election, a lot of fake news came into question. It's certainly a big topic today. You have videos, you have news that are being reported. You don't know if they're fake, if they're real, if it's a picture that's been modified or it's a picture that's been staged. It's a big topic. I think it's a topic that in the academic community we don't pay as much attention as we need to, but certainly out there in industry, people are looking at it. Then in 2018, all the talk was all these predictive systems, for setting bail, for deciding whether someone should get into a school. People were talking about using AI, using deep neural nets for making these decisions in a way that's not necessarily explainable, but seems to be very efficient and seems to work well on good data sets. But then people in the legal arena, especially with the bail example, were very suspicious because they're saying these are unfair. It's not clear that these algorithms, which are unexplainable and untransparent, are going to be fair against minority groups, against disadvantaged people economically, and so forth. So this is just an example that in California, there was this thing on the ballot whether cash bail will be replaced by bail, no bail. Just a system involves no money, and that seems to be much fairer to people who are poor. But in addition to that, the proposal was that there will be an automated system that gives sort of the recommendation to the judge whether someone should be released on bail or not. And then ACLU and a lot of, actually people you would think that would be before this, because it meant that there's no more cash bail, were against it. We're saying, algorithms are nowhere near a situation where we should trust their recommendations. And there, in 2018, there was a whole there were a bunch of workshops, and there was a whole semester assignments that talked about this issue, fairness in machine learning. And in some sense, it seems like we were quite naive at the time talking about the bail system, because now these AI systems are sort of, people are so fascinated by them, they're being unleashed, and the whole big question is AI safe? So one is talking about trustworthiness, both in terms of the correctness of the facts, okay, and or predictions, but also in terms of safety, like what is this thing going to cause down the line? And that people haven't been really defined what trustworthy means, and I understand that several people in Penn are actually very interested in this problem. How do you define trustworthy AI? How do you detect it? This is a sign on the way. If you go drive from Berkeley, I guess in the direction of San Francisco, there's this AI company called Hive, and they themselves, they're an AI company, but they're saying, listen, we are actually going to tell you what's real or not. So we are not that we are going to generate fake things, but we will tell you whether something is fake or not. So come to us to see whether what has come up here is a real image, or maybe an image that was generated by some generative AI. So you know this. So trust is a big question these days. And the thesis of this talk is that given that we have some sort of recipe that enables us to trust technology for cryptographic tasks, maybe we can try to use this recipe for the machine learning world. So again, the same recipe. We have a task, except it's going to be a machine learning task, so it's not going to be encrypting. It might be running some sort of prediction system. It might be running a risk score system, or maybe a generative AI system. We're going to model an adversary, okay? We are going to define what is a good enough solution, and then we'll build a trustworthy solution. Trustworthy here will be the thing that we define a line above it. And then, again, we should have proofs. So we could make some assumptions, maybe different assumptions in the cryptographic setting, but assumptions that we believe in, or at least that we feel we can scrutinize. And we will show that under those assumptions, our solution is trustworthy. Okay, so this is I always use this, picture, meaning that obviously I know how to do this. So to me, everything looks like a nail. But I think that even though machine learning, AI, doesn't really, it's not defined only when an adversary is around. So in the encryption case, we want to communicate privately. The only reason we use encryption is because we think there's an adversary. Machine learning is important without an adversary. The fact that we can predict pictures, whether it's a cat or a dog, or approve loans, we don't necessarily think about an adversary lurking in the system. And yet, the stakes are so high, and these are very attractive targets, that thinking about an adversary in the system is probably a good idea. So not assuming that we know what are the risks around, but trying to think of a worst case adversary in some sense would be a good idea when we are trying to prove trustworthiness. Now, when I talk about worst case adversary, I'm going to use the cryptographic type of model, which is the adversary. I don't know its strategy, but I am assuming some time bound on the complexity of the adversary. It's not going to be able to run in exponential time, but it will run in efficient time, polynomial time. So I'm going to use the same aesthetics, but you could imagine that maybe down the line you will try to think of a much more fine-grained adversary that is able to use a certain amount of processors in a certain amount of time, and for such an adversary I'm secure. And in the future I have to enhance my system if I want to be secure against the more modern adversaries. You with me? Okay, so I'm not going to make assumptions on the strategy, but I will assume computation limit on the adversary's time. So this sets the ground for this talk. And I will try to convince you that this is an interesting way to think about the machine learning space, about trustworthiness in the machine learning space, by having a several examples during the development of an AI algorithm, post-development when I want to maybe verify a model that has been trained, and then also when we think about the future, when the model is used and there might be out of distribution inputs. So I've trained on a certain distribution of inputs, training data. I'll use it possibly on different training data, and maybe before I jump using it, I should verify the model that I was given. So I'll show you adversaries for all three stages, and how we use this cryptographic approach to address these adversaries. So let's start with the training phase. But I just want to say that, it's interesting because I've been in this computer science world for a long time. And I started at MIT in the 80s. And at that time, all the systems people said that theory is irrelevant. Because, and by now, in algorithms, and by now they don't say that because a lot of the big inventions out there, search and content distribution and so forth, are actually based on some theoretical algorithms. But now there's the difference between AI theory and AI practice, and somewhat of a similar thing that I witness, at least from far apart, that there's the theory and there's the practice, and one can always say that the theory is impractical. But at least for my talk, I can say that there are adversaries applied to both. You can talk about adversaries in theory, and there's definitely adversaries in practice. So if we come up with some theoretical ideas of how to define and deal with adversaries, they probably will have some benefit for practice. So the methods could apply both to theory and to practice, and definitions would apply to both. Hopefully, what is certain is the adversaries apply both in theory and in practice. So I am going to sort of take a black box approach. So for this talk, I'm going to talk about training algorithms, and then I'm just going to use, this idea that I have maybe pairs of data, so there's an X and a label Y. Sometimes it's unsupervised, so there is no Y. And they're a member of some distribution D. Sometimes this distribution will change, but usually D will be present. And this data comes possibly from many different sources, possibly from one source. And then there's some sort of training algorithm to take place, and the output is always going to be H in this talk. So it's going to be some model. So this could be an LLM, it could be a predictive system, but it could be just a regression, but I call it H. And what I want is to essentially, my goal is that there's some sort of loss, which is the difference between how well this H takes X to Y. So H is going to be an algorithm, which takes input X and gives label Y. And I'd like to say that this H does well with respect to the true labels Y for general loss functions. The simplest thing is just I'd like to minimize the difference between H of X and Y. H of X should equal to Y, then I say it's correct. But it could be other loss functions. So this is when we talk about training, just for notation setting. I'm always talking about X is part of the distribution, and Y is a label. And then I'll also talk about inference a little bit, mostly about training. And there I have an X that fits into H and Y comes out. But X now could be a member of a different distribution. It's not distributed according to D. So I'm really thinking here about D being the marginal distribution on the X's. Maybe it's part of D prime, and my H gives me an answer. Again, I would like to be as general as possible. So the answer could be 0, 1. It could be a percentage, a risk. It could be a sequence. It could be a distribution over sequences and so forth. So kind of the paradigm could apply to a lot of settings. Okay, so what are the adversaries that one could consider? There are probably many, but here are two very clear adversaries during the training time. So one adversary could be the trainer itself. So let's say the data is coming from outside sources, and you, as someone who's contributing data, or a hospital, someone who's contributing data, or maybe a credit company that goes to some AI vendor and gives them the data, they want to keep the privacy of the data. And let's say that this trainer is not to be trusted. So a very obvious question is, can we keep privacy and still train? And the other question would be, what if the data owners are adversarial? So the people who are contributing data might do data poisoning. People probably have asked it because with their goal is somehow to screw this H so that it will be bad towards some individuals or classes of individuals. And let's start with this, with the privacy. So privacy is kind of the obvious one to start with as a cryptographer. It's also, we have a lot of beautiful tools, and they perform better in theory than in practice. But I think that, again, I think often people make the mistake to say, they're good in theory, but they're worthless in practice. And this is a mistake that people do again and again. It is not true, and they have made a lot of progress over the years, and I'll show you some of this progress. Are we good? People can raise their hand if they want to. Okay, so back to if we wanted to cast it in terms of that recipe, we would like to get private training. The adversary for this particular slide, he's honest, but curious trainer, so he doesn't change anything. He will follow the recipe, but he's very curious about the inputs that he got. And what we would say is that the solution is good enough if the adversary cannot learn more about the data than the output H reveals. Now, those of you who've done differential privacy, which I know there's certainly people in Penn, a lot of people who've done it, realize that this is weaker than differential privacy. Differential privacy says that you can't even tell whether a particular data item, X, Y, was present in the training data or not. But it can be, once you see what I do here, differential privacy can be incorporated. Okay, so right now all I'm saying is this. At the end, there will be output H, okay? And you'd like the trainer to not know more about the input values than H is. If H just summarize all the input values, obviously it's going to know, and I don't prevent it. Okay? So that's my definition. Okay, so as I said, there's lots and lots of crypto. Secret sharing, multi-party computation, private information retrieval, homomorphic encryption, function secret sharing. Over the years, we've many tools in cryptography which could be useful for this task. And indeed, there's essentially two paradigms for how people have suggested to achieve privacy during the training phase. And these, very quickly, I know most people here, or there's some subset of people here who know this, and I think it's a large subset. So what happens in training? There's data providers, and there is, this is one model. It's called the multi-party computation model. So here the idea is this. There are, let's say, 2 servers. You see these 2 servers. There might be 5 servers. There might be 7 servers. The point being in the 2 is that they don't collaborate with each other. You might not trust them individually, but you trust that they don't collaborate with each other to reveal to each other what they know. If there are 3, you might not trust 1. If there are 5, so you could talk about majorities here. But let's just for now for 2. And every data provider, people who have X and Y, they go through some sort of secret sharing. That should be not sherry, but sharing. It's amazing how every version, mistakes keep coming, even though I fix them. It's a miracle of PowerPoint or of my use of it. In any case, there's a way to break down your input. You give one share to one server, another share to another one. And what they do now is they go through an algorithm where they take an original algorithm, which did not worry about privacy, and compile it into a kind of a different algorithm, which is an interactive protocol between these 2 servers, where each one has just a share, and they based on the share, they send messages, they get answers, and at the end, they will all hold shares of H. And then they will tell each other what the share of H is, and they will reconstruct H. Now, so there's sort of 2-party secure, and then there is a reconstruction phase. And the assumptions that we know how to do this on is 1, that these 2 servers don't talk to each other, so that's a trust assumption, okay? And 2, some computational assumptions. So you're using some sort of cryptography or a computational assumption, and you could do it based on factoring, based on learning with errors, which is one of these problems where you have a system of equations, which are noisy linear equations, and you use the parameters and the noise in such a way that we absolutely don't have any idea of how to solve these system of linear equations. Even though if there was no noise, it would be just Gaussian elimination, you could solve it, okay? And this is a hard problem. It's connected to some problem, a classical problem on integer lattices, finding shorter vectors, but let's just call it LWE for now, learning with errors. This is factoring, learning with errors. So those are the assumptions. So what's another paradigm? Another paradigm is homomorphic encryption. So this is started in 2008 with a paper of Gentry, and what happens here is, again, you've got the data, but now instead of just giving X and Y and splitting into shares, you encrypt X and Y. So there's some encryption method that you can encrypt X and Y. You never decrypt it, but you can, what the invention is, that it's possible to take any training algorithm and run it in this mode where it actually runs on encrypted values. And so let's say if you think about the training algorithm as a circuit, arithmetic circuit, where there's pluses and times, then now you're doing these, you add encryptions of X's, or you multiply encryption of X's, and then you do some other tricks in order to be able to do this for many repeated multiplications, many repeated additions, and at the end, there's an encryption of the H. So the server at this point, who was running this encrypted, he has never been able to decrypt a single encryption of X and Y. So still, you have to be able to figure out what H is. Then you have another thing where there's some decryption key, and the shares of the decryption key are held by, let's say, 3 different parties or 5 different parties, and they come together to reconstruct H. Okay, so actually, if you think about it, you know, there's an encryption stage, there's a decryption stage. The assumptions are the same. So first is that there exists a homomorphic encryption scheme, and in fact, we know how to do this under learning with errors. And second, that these shareholders of the key don't collaborate. So fundamentally, the assumptions are the same. The methods are not the same. Their achievement in terms of how much communication they require, what is their efficiency are different. And there's this tension all the time between people who say multi-party is better, or homomorphic encryption is better. Usually the multi-party computation is worse on communication because there's a lot more communication. Whereas here, there's very little communication. You encrypt, you give it to the server, it runs, and then you decrypt. But computationally, these are usually more intensive. All right, so what's the challenge? Sounds wonderful. I gave you 2 solutions. So it turns out that, in fact, these solutions can be used for the inference stage. So when you already have the H, and you just want to encrypt your X, say, and run the H and get the answer Y, these things are fairly efficient. But when you want to do training, even though in theory you could do either the multi-party solution or the homomorphic encryption solution, scale kills you. So because we're, in training, you have to do many iterations on data batches, and everything is encrypted, or it's a multi-party computation, scale is a big problem, since you know that we have to train on lots of data. So if you want to talk about scale, you can think maybe of other axes, but here are 3 important axes. One of them is who the adversary is. So it could be just an honest adversary who follows the protocol, but he's curious about your data. Sometimes people think about malicious adversaries. It doesn't even follow the protocol. Then the axis could be, what is the computation? Is it a linear regression? Is it logistic regression? Is it a neural net? How many layers of the neural net? Is it an LLM? These are, as we keep going, these are more and more complicated computations. And the third axis would be, what is the assumption? Are we just assuming that learning with error is a hard problem? Are we assuming that there's multiple parties and they don't collaborate? Maybe we're assuming that there is trusted hardware. And again, the reason I put them here, I would say the computational hardness in my mind is a good assumption, better than no collaboration. And no collaboration is better than trusted hardware. When you talk about scale and when you try to attack this, you choose yourself some points on these 3 axes and you try to solve, try to show that you can scale for that particular setting of the adversary, of the assumption, and of the computation. So I just want to say a word about the hardware, and then we'll go and talk about the kind of solutions that I am working with, which make assumptions on the computational assumptions, and maybe on the collaboration. So what kind of trusted hardware are out there? So Intel SGX has been around for a long time, 2015. The new player these days is this NVIDIA H100 GPU, but for both of them, there's similar discussion or guarantees. So there are sort of 2 boxes here. Box on the left is essentially what comes in is, let's say, an encrypted piece of data, okay? If we think about it in the context of machine learning, then inside of the box it gets decrypted, so the box knows a key. Then you do some computation on this, and then let's think of it as H, if you like. The entire H is in there. You compute, you train. So actually not H. If we're in the training phase, let's say the XY pairs come in, you do a little bit of training, something comes out, then, and you keep going this way. But inside of the perimeters of the box, the assumption is nobody sees the X and Y, nobody sees intermediate results, and this is how you proceed, okay? And the second box, which both in the Intel case and in NVIDIA's case, is that they add even a way to prove. So the box actually outputs to you a proof that the computation that was done is done correctly, okay? So, but a proof doesn't necessarily leak anything. So it might be a zero-knowledge proof or some sort of certificate that leaks very little on the intermediate computation. So it won't be a trace of the whole execution, obviously. There will be some proof about the result versus input versus output. Okay, so what's wrong with this? This is wonderful, right? Why don't we just assume that we have trusted hardware, just put in all the encrypted X, Ys, and finally comes out the model. I think it sounds good, except the history of trusted hardware is that you shouldn't really trust it because there's a lot of side channel attacks. People leave, if you run it on 2 inputs, there's some trace of the previous computation. People have even managed to do all kinds of physical attacks, monitoring the power usage and other things to actually reconfigure the secret key. So this is sort of a black box that if we're talking in a university environment where we are trying to actually prove that these things work, if we just assume that this works, that we haven't done anything. But this is not to say that this might be eventually the way to go if it has gotten enough scrutiny. Okay? So now that I've said what the secure hardware is, I'm going to leave it alone. And I'm going to say, what can we do if we don't go to secure hardware and we just use computational assumption? On those axes, the adversary, computation, and assumption. So one place that has been a lot of work is in the area of GWAS, genome-wide association studies. So why? Because this is an area where sort of almost by definition, by looking at the sequences, you can yourself already discover something about the holder, even if you didn't have their name next to it. So even when things are anonymized, the sequence itself is revealing about the patient. And there's this famous article with Yannick Ehrlich and others where they could say you can identify personal genomes by surname inferences. So you could sort of show that through the genomic sequence you belong to a certain a family, and then if there's some other database that contains some information of that family, you can use that side information to retrace who was the owner of the genomic sequence. That's on one hand. That's why it makes it an interesting test case, because you know that the data itself, even when it's anonymized, is revealing. And 2, scale is everything. So essentially, there's a whole bunch of diseases, starting with schizophrenia, but you see here Crohn's disease, breast cancer, where when you do these GWAS studies, if you only have a few thousand of genomes, it's pointless. You need really 20, 30, 40, 50, 60,000 in order to get the right correlation between genotype and phenotype and find the alleles that are implicated. So scale is an issue. Scale is an issue, privacy is an issue. It made it a perfect problem to study. And people have studied it both from the multi-party computation world. So there's a paper by Cho, Hu, and Bonnie Berger's group, a secure genome-wide association analysis using multi-party computation. So they look at the 2-server case. They think about these XYs, so now let's think about it as data. This is like a genomic sequence, and it doesn't come really from individuals, but it's individuals going to, let's say, I don't know, the Broad or some other medical center and getting their genome sequenced. So there's a few participants that hold lots of data, and they give their data, let's say, to these 2 servers. They run GWAS on the shares. So this is just an instantiation of how the multi-party or the 2-party computation. So there are 2 servers, they run the GWAS, and they get reasonable results. I think they used 100,000 patients with 500,000 SNP, or 5, so I have the exact, I printed it out just so that I don't do them a disservice. If people are interested, I could give you the exact numbers later. But it does pretty well. When we say pretty well, one of the things that I noticed here is they say that something took 80 days, and they compared, and they said 80 days is not bad, because they were comparing it to the legal, to how much time it took to go through lawyers and get NDAs signed, and that also took 80 days. So they're saying, well, if you want to do away with the lawyers and use a computational method that uses multi-party computation, it's about the same time. But the interesting thing, and this is what I have on the slide here, is that at that time they said, look, the one problem with our solution is that there's a lot of communication. So the GWAS requires a lot of communication. The communication also is proportional to the number of servers. Here there are 2 servers. If there were more servers, it would be even worse. And they said alternative cryptographic frameworks for secure computation, such as homomorphic encryption, currently impose an overwhelming computational burden, many years of computation or petabytes of communication at the scale of 1 million genomes. But But actually, 2 years later, there's a paper that I'm part of from Duality, a secure large-scale genome-wide association using homomorphic encryption. So we use very similar, same diseases, and we use homomorphic encryption, so communication now is not going to be a problem because everybody just encrypt, and then we do everything under encryption, and we do actually a factor of like 10 better than them in terms of time. What this one people are interested in can read the paper specifically, but what this teaches you is that things really improve as time goes along, and you can do the same computation on the same size databases, and the time is so much faster, and the extrapolation of what's going to be in the future is even much better than that. So you go on, the difference is between days to hours, or hours to seconds, depending on what your starting point was. I think this is a good place to look at. If people are interested in the privacy question is in the genome GWAS space. I want to mention one other paper on privacy. One thing I wanted to say is that in the case of homomorphic encryption, if in fact you only have a few centers, okay, you could think of those centers who are encrypting their data as also the ones who hold parts of the key. So you could sort of identify between the people who are contributing the data and the people who are holding part of the key, but their multi-party computation between them will only be in the key stage, okay? And that might so you sort of shouldn't duplicate necessarily who holds the keys and who the centers are. You could identify them. All right, so I want to mention one more piece of work in the space on privacy, and then we'll move on to verification. And that is some newer work just from last year, which is, talks about not genome-wide association study. It takes oncological data from, whereas the other ones run on sort of these well-known benchmark sets. This is really coming out of a hospital, Ichilov in Israel, and the kind of things that they were interested was a chi-squared, survival curves, and a whole bunch of things that these clinicians anywhere are interested in doing. And the question is, could we do it under homomorphic encryption? And the answer was yes. And another thing that was interesting here, not just that the data was from real patients, but that we addressed joint operations rather than just, so in other words, rather than just getting more and more patients, all of which have the same sort of type of data, like genome sequences, you want to look at cases where the data may come from hospitals, from pharmacies, from different doctors, and it's the same patient, but there's different columns of information from different centers, and you'd like to do joint operations. So here it's very important that anonymization won't work for you, anonymizing the name, because you have to be able to link records about the same patients from different sources. So the ability here was to do join, and this picture, I guess, shows it. So like you're having different features on the same patients, and this was a way to combine it all under encryption. The key sort of theoretical insight here is something called interactive bootstrapping. So how many of you have heard about bootstrapping in homomorphic encryption? Some of you, probably the theory people. So in order to make homomorphic encryption, the brilliant idea of Gentry, which is survived all the works, is the reason why we can do arbitrary computation under encryption is because he had this encryption scheme which had noise in it. Every time you're adding or multiplying, you made the encryption a bit more noisy. So you could still decrypt, but after you did many operations, you wouldn't be able to decrypt anymore. So then how would you be able to do an arbitrary amount of computation? You know, because he wanted to say that you could do any computation under encryption. And he had this idea how he could, every few operations, when the noise got to be too big, he would in a sense, decrypt under encryption. So he would sort of recover the original message and re-encrypt it. So incredibly clever. It's called bootstrapping. It's like genius. It's one of those ideas that, wow. And as good as it is, this is where the slowness is. Every time you do bootstrapping, it slows down the encrypted computation. So the kind of theory idea here was how to do bootstrapping faster, and it essentially was interactive. So there's some combination here between homomorphic encryption and interactive protocols between the data providers, and which this is where the efficiency came out of. I guess more important than this particular study, there's a tool set there. There is chi-squared, mean, median, survival analysis, logistic regression, training over encrypted data. So there's something out there that can be used for doing this type of computations and joins. Yeah?
So you said earlier, right, you pointed out earlier that all this is sidestepping the question of what the output actually reveals in
Right, absolutely.
And of course, as you probably are aware, right, there's this whole very active parallel literature on exploring the extent to which machine learning is vulnerable to things like membership inference attacks,
DP,
reconstruction attacks.
right.
And so my question is sort of, that literature seems to be, not reassuring, right? So in general,
Right, from the machine learning algorithm, you could learn a lot about the personal
yeah,
data.
yeah. And so what do you, so in some sense, right, pending the outcome of that literature, it could be that all the things you're describing are that the weak link isn't here, it's just in the output itself.
It could be.
And I'm wondering what your opinion is on that.
So very good, very good. So I prepared for that. I say maybe that's not good enough. Not good enough of a solution because given H, you shouldn't learn, and all this literature says that you can learn, okay? So then you've got the differential privacy definitions where you want this extra strong guarantee that from H you shouldn't learn, and assuming that you believe that differential privacy is the way to go, then really what it is you want to have your training algorithm be a DP training algorithm. But the method of either using multi-party computation or homomorphic encryption can be applied to a training algorithm which is a DP training algorithm. So whatever tricks you've used for addressing the utility versus privacy, okay, whatever your analysis there, it doesn't really, it's like, it doesn't interfere with doing your entire algorithm under encryption.
Yeah, I agree with you in principle. I guess I was asking.
Okay, so if your question is, have we done implementations with DP? No, I haven't.
Well, my point was going to be that even DP training of a large language model appears to be completely infeasible.
Right, and this is not a large language model. So the question even is DP training of, well, well, you asked it, but DP in the context of GWAS, okay, doesn't make much sense. Because the whole point about DP is the type of queries are not the type of queries that you do in GWAS. The dimension of the genome versus the noise, but so it's a good question whether for computations where DP does make sense and you have a good trade-off between utility and privacy, these things can be efficient or not. Okay, we'll get to that, but I hope that it's not a great answer because I don't have cases that I've analyzed running time.
I guess maybe the short version of it is that when I think about the composition of differential privacy and homomorphic encryption in deep learning, it strikes me as kind of...
In fact, when you think about deep learning, if you're talking about training, it's already, it's already very expensive. Yeah, but okay, so the question is, what do you do? Do you try to train the entire thing? Do you try to find components of it that you should train under encryption and do differential privacy? Excellent question. But I didn't even claim that you could do deep learning training. You could do inference, but training, much more difficult problem. So but that's why I chose a specific problem like GWAS. And you could add DP to it, but as far as I understand, DP is not really the right solution for genomic analysis.
I think for is not for the same reasons like U.S. Golden State Killer case where the killer was identified because their relatives had uploaded their genome to whatever it is, 23andMe, and differential privacy doesn't say anything about the risk that you share, that you suffer from the fact that you share genetic material with other people. Like that's you're not.
I see.
Your data isn't even.
I thought it would, no? Because isn't it for not just for individual, but for actually groups of individuals? You can't tell if they belong or not belong in a data set?
I mean, there is a, like if you have K groups of size K, you have something that
I see. Okay.
K, but
Okay. All right. In that case, it's a naive answer to say just take a DP training and apply it. But as theoretical blueprint, it's reasonable. The question of whether this thing would scale up or not is, it's a very good question. Here, all I was going to say is that there are other uses for this. I describe a medical example, but there are other uses. At MIT, there is this thing called Scram, where there's a whole bunch of companies that come together and they tell each other, they don't want to tell each other, that they had some viruses and they had some cyber breach and they've lost all the customers' data. But they would like to find out what they should watch for. So they do some multi-party collaboration on security breaches, and then they do some sort of statistics, and then they tell people about what to watch for in the future. And you could do this either in a multi-party setting or with a FHE. So that's another setting where it's actually very important probably to aggregate information, and on the other hand, not to necessarily tell each other your private information. Okay, let's move ahead. I am going to skip this and talk about verification. Okay, so we just talked about during development and we just talked about privacy. Let's talk about verification. So what is the goal in verifying? So let's say that there's an H, and what I'd like to do is I'd like to be able to verify what the, let's say I gave my data to some company who sells this incredible, machine learning capabilities, and they claim they gave me back a wonderful model. It's fair, it's accurate, it's robust. Well, I could choose to believe them, or I could try to go through a verification stage. And when I say verify, I would like to, of course, verify it cheaply. I don't want to retrain. So I want to be able to verify with fewer data samples. I might want to not have such great data. Maybe my data is noisy. Maybe I just have random samples and I can't do adaptive questions. And I'd like to be much more efficient in verification. And who's the adversary here? So again, the adversary now, when I gave my data to someone to train for me, the adversary could be the trainer. Maybe the trainer gives me, because he wants to do a really fast job, he doesn't want to use a lot of resources, maybe he gives me back an H, which isn't very good, okay? So what is it that I'd like to verify? Many possible properties. As I said, quality, robustness. Do they use the right data? Are they adhering to regulations? Because later on, I will be responsible, not necessarily the vendor that sent me the model. Okay, so when we talk about verification in general, this is a slide we always put up. There was a paper, I think this is a paper by maybe Babai et al., where they said, in the future, a single reliable PC will be able to monitor the operation of a herd of supercomputers with powerful but unreliable software and untested hardware. So the image was that you'll be able to verify something happening in cloud computing all over the world with very, very simple technology. So verification will be much simpler than what computation is. And we have a lot of works that indicate that maybe this is not such a dream. So we have interactive proofs, zero-knowledge proofs, probabilistically checkable proofs, delegations, patch verification. There's many generations at this point, maybe 3-4 generations of students who are writing papers, who are getting tenured in famous universities, who dedicate their career to this, okay? So you would think that verifying properties in the machine learning space will be just as, we can use all that technology, all that mathematics to verify. The problem is that the problem in machine learning is not the same problem. So whereas usually in the previous slide, you've got sort of a prover who has a program and a verifier who wants to check that the prover really executed the program they claim they did. They both can see the input. And not only that they both can see the input, so that the program or the server says, this is the program I've run. Let's say I sign the document and I want you now to verify this is a legal signature. In the context of like blockchains, they always talk about verifying signatures. So you know what the verification algorithm is, you know what the message signature pair is, and now you check that it is a valid signature. But in the ML space, I guess that's not the story. The story is, first of all, is that we have access to data, right? And the more data, the better. The program, or whether it's Google or OpenAI or Facebook or whatever, they have access to tons of data. They train a model, and now they want to prove to me that this is a good model. So it's not even, since the ground truth is not even known, since the ground truth is what they learn from the data. It's not always the case that this is clearly labeled by some function, and now they are just coming up with a faster way to implement this function. They don't even know what the function is. So the rules are different. We're getting samples from an input distribution rather than an input that we can both read. The samples that the OpenAI and so forth have are different than the samples that the verifier has. They certainly have a lot more data than the verifier can sample. And That's one difference. The compute is randomized, which is usually the compute that we think about in all this literature is deterministic. It's massively parallel, so it's happening in parallel rather than on one single sequential circuit. And as I said, the ground truth is not pre-specified. So we need even a new definition of what it means to say that if you hand me an H after you've trained on data, that it's a good H, okay? So there's here is a definition. So this is a definition, it's called pack verification. It's with my student Jonathan Schaefer and Guy Rothblum and Emilio Dayoff. Here is a possible definition. So we're going to say that a learning class is pack verifiable. So what's a learning class? We can think of decision trees, we can think of neural nets of a certain depth, we can think of hyperplanes, but we want to talk about whether you can actually verify hypotheses from a class, okay? And what does it even mean to verify them, okay? So the definition is this. We'll say that you can, if somebody sends you over a decision tree or sends you over a neural net or a hyperplane, you'll be able to say that you can prove to someone that it's a good H, okay, means that you can engage in a protocol after which the protocol will be both complete and sound. What do I mean by complete? Here's a definition. It says that if the verifier will be convinced to accept the model, if in fact the loss of this model, okay, so there's an H, there is a loss that could be, the difference of whether H is correct or incorrect, okay, that the loss of this model is not too far from the optimal model in this class. So let's say that there's an optimal decision tree to solve this problem, and it has a certain loss. I'm thinking of an unrealizable case. So it's not that there exists a perfect decision tree. Every decision tree will make a mistake. There's the best decision tree, but there's the one that this particular prover is sending me. So I want to say, if they can convince me, so that they should be able to convince me when the loss of the decision tree that they send me is not too far from the loss of the best decision tree, and they should not be able to convince me, that's the soundness, no prover, no matter how clever they are, as long as they run in polynomial time, should be able to convince me that, to accept their decision tree if the loss of this decision tree is much further than the optimal. Okay, so I'm comparing myself. I want to prove to you that I'm as good as a model could be. Now, who are you as a verifier? As a verifier, the most important thing in this definition is that you'll be more efficient than the prover. Otherwise, you would do it by yourself and you don't need anybody. What does it mean more efficient? Well, I want to enlarge the definition of efficient. Efficient could be that the sample size is smaller. So they also have some data, that they have less data. It could be that the quality of the sample is worse. So there might be as much data, but it's bad data. And it could be that maybe they have random samples, whereas the prover has the ability to conduct experiments to do adaptive sampling. So given an X, you give an X, you get back a Y. Now you give a different X, and you get back a Y. And this is an ability you have, which is different than you just get a bunch of XYs, and you cannot adaptively change the X's. Okay. So again, if we want to think about the book, the task is might be to verify that the hypothesis that you got, like the decision tree and the classical decision trees of a certain size, is high quality. The adversary is some prover, okay, who wants to work less maybe, or he wants to give you a bad H and get paid. And we would say that a good enough solution is that you will be able to verify that H is within an additive error of the best H that can be given. Okay, it's a definition. And what can you do with it? So again, the challenge is going to be, if in fact there's a perfect decision tree, all you do is you test it on some questions. If it's not perfect, you get a mistake. Okay, but in a non-realizable case, there is no perfect decision tree. Using the decision tree example. So what you need to you need to be able to verify this inequality. Now, it's easy to estimate how well the decision tree they gave you is doing on random samples that you have X and Y. So you see whether the decision tree is giving you the right Y. But what you don't know what the optimal is. So the question is, can you verify this equation even without knowing what the optimal is? And essentially, there's a bunch of results, but one of them is that if you look at these class of Fourier sparse Boolean functions, so if you look at a Boolean function, look at this, it's a Fourier representation, and there's only a few non-zero coefficients, or it can be approximated by something that has few non-zero coefficients, when decision trees fall in this characterization, then you can do this complete and sound pack verifiable scheme, where the prover, he runs the best algorithm we know, which actually needs a membership query, so it needs adaptive queries. It gives X, gets a Y, gives another X, gets a Y, but the verifier only can use random samples. And under the assumption that learning parity with noise is hard, verification is strictly easier than actually proving. So there is a difference here between the prover and the verifier, provably so, under this computational assumption. So in other words, there is a way to verify the quality of the decision tree or the Boolean sparse function only using random samples. I'm almost out of time, but I have to get to the kind of...
You're also saying that
yeah.
there's a fast proof in your optimality if you have queries.
But I can verify it with random samples. Yes, and that's we know. So yes. Okay. So not only that I can run the reconstruction of those coefficients, the non-zero coefficients of the representation, but I can also prove to you that I will make you accept if I'm close to the optimal, and I will not be able to make you accept if I'm far from the optimal. Okay, so I want to still get something. I'm going to steal 5 more minutes. I verified this competitive quality. There's a new paper that Guy Rockland talked about in this fairness about verifying distributional properties. So here I verified that it was competitive, let's say, with the best decision tree in the example that I was talking about. But what I want to say is, how about verifying robustness? So we talked about privacy, we talked about verifying quality. How about robustness, a big topic? How do you show, or can you show, that a model is robust? Now, we all know there's adversarial examples, you can't avoid them, but I'm saying, can you do, at least with, let's say that every algorithm has adversarial examples you cannot avoid. I will show you that there's a much worse attack than that. Okay, so it's not the regular adversarial example. So here's what I will show you, is that an adversary who's is able to trick you so that you won't be able to verify whether a model deviates from the ground truth on perturbed inputs. So in other words, there's the real inputs. The model will work well on inputs which are distributed properly, but there will be some small tweak of the inputs where you won't be able to detect that the model deviates from how it should behave. So this is the picture. We have a client. The client will send its data to a trainer. The trainer is an adversary. That's those red things. And he will give back the machine learning model to the client. It will be and this model will be a bad model. It will be non-robust in a very strong sense, and it won't be detectable. So essentially, we look at this example. There's a bank, and let's say the bank goes to some AI service company, and it says, listen, I want you to come up with an AI system because I'm sick and tired of having to read through all these loan applications. So I'll tell you, here's an example of all my back history, which loans I accept, you should accept, which loans you should reject. So green is accept, red is reject. And the company comes back with a model, sends it back to you. It accepts the right loans, it rejects the wrong loans. And what we think of an attack, the attack is that the AI company, they are very happy to come up with machine learning loan programs, but they want to be able to get loans in the future. They, their family, their relatives, and so forth. So we think about this key. What they're going to do is going to put some backdoor inside the model so that now, even though their loan should be rejected, they know how to select it. So they've changed the model with this little orange thing. And now they know how to take their loan and modify it ever so slightly by this epsilon perturbation. So in the future, essentially the same loan will be rejected. Accepted. Should have been rejected, but it is accepted. So some slide here disappeared. Which slide? Right, this one is, should have been rejected, but it is accepted. And furthermore, the backdoor, okay, so now there's the client. He has this model. There's a backdoor in it, okay? So maybe now you know that it could be backdoors. You should look at it and find the backdoor. So the interesting part is that we could show that the backdoor is undetectable. So whereas previously we could maybe hope for lots of things, now I will show under cryptographic assumption that you cannot detect the backdoor. So what does that undetectable mean? It means that if you look at the training that was honest versus the backdoor training, okay, and you are giving, and now you are able to use this model. You could put in loans and see if they accept or reject. You can tweak them, see if they get accepted or rejected. You won't be able to tell apart whether you're using a true training, an H that came out of an honest training algorithm or a backdoor training algorithm. And how is this always the case? So we can always, for every neural net, we can show that you can plant an undetectable backdoor such that you can, if you knew the backdoor, tweak your x to an x prime, which is close, such a decision is reversed, but you cannot detect it. And there's sort of two results. One is a black box result. What does black box mean here is that the access that you have to try to figure out whether this model is has been backdoored or not, is that you just submit X's and you get back answers. So under the fact that there's only black box access, which is a restriction on you trying to detect, right? It's a big restriction because you actually have the model, usually. Under this restriction, we can show that every neural net can be backdoored in an undetectable fashion. And the idea is very, very simple. So, you know, like Michael, I think, already in his PhD in like 1980, something, would have thought of it. We should not name numbers, right? Let's say 89. Is that you take whatever neural net is and you add to it a little module which is signature verification. So, and now when you put your X's in, if you know what the backdoor is, you add in some location sort of a signature of the rest of the location. And when you enter in, you check, is there a signature there of the, you know, and if there's a signature, you can verify if there's a signature there, you accept, otherwise you reject. And the thing is that it turns out that there are signature schemes that can be written down as a very small neural nets, you know, 4 layers based on some geometry problem. And then that's what you would put in here. Okay, but black box, you could say, black box, that's not very interesting. So there are even results on some white box. So this is not for every neural net, but for this neural net where there's random features, where you choose random features, and then you do a hyperplane, and then you get the results. So it's one layer, and then a hyperplane, where even if I gave you the weights of the neural net, so I gave you total white box axis, or white axis, whatever it is called, then we could still plant a backdoor that will reverse your decisions, and still for you to tweak only an epsilon fraction of the locations. And what's nice about this particular result is that it's no longer adding a verification digital signature, but it is actually, instead of using random selection of the feature, random weights in a sense, you use a pseudo-random distribution for selecting the features. This pseudo-random sequence is cryptographically indistinguishable from random one, and what it will do is essentially put weight on certain locations, and if you knew where that was, you would modify your input accordingly. Yes, yeah.
So is it the case that this, that this signature that I put in the input to get the loan, is there some sense in which it isn't modifying meaningful features in, say, the loan application? So, I mean, I could always make sure that I get a loan by lying about my income, my educational background, my savings. So just getting a model that is doing a good job at loan prediction, it's easy for me to get my loan approved by lying. And so I think what you would want, right, is a backdoor that's sort of undetectable in the economic sense.
Okay, so it's a theory result, right? So we're saying that you can go from X, which is loan, to X prime, which is a perturbed loan, where the distance, the Hamming distance between them is like n to the epsilon, where epsilon is sort of as small as you choose. And you are asking for an interpretation of it sort of in the real world. In terms of lying, we're all sort of assuming that there's some sort of ground truth, right? And translating this, I think that the truth is that when we talk about prediction of loans, they're all going to go and embed it in some sort of lower dimension of space. So it's no longer that you're really reading if it's Michael Kearns and reads in a certain address, but we're going to some geometric interpretation that there, it's not so clear that people are so versed in understanding what the geometric representation even means. Anyway, what are the takeaways from this? First of all, you have to beware of bad randomness. So I know that Nadia Henninger was part of your faculty, and she had all these famous papers where you had bad randomness, you could break RSA because people had correlated randomness. Also here, if somebody else is dictating your randomness, then this shows that they can actually dictate de facto, they are putting a backdoor into your system, even without you knowing. Second takeaway is that you should always process. If somebody gives you a system, I would not assume that it works. You should try to do something to take the system and do something else. We've tried like running gradient descent, more iterations. That doesn't work, actually. It doesn't destroy the signature, example. You could do randomized smoothing, right? You could take your X and kind of smooth it and run that, but the amount of sort of adding noise to it, the amount of noise has to be less than the amount of change that you've made. So it's not clear that would work either. So we have some new work that says that for the same class of Fourier sparse function, you can actually take a model that may have been backdoored and now retrain. Okay, so retraining seems crazy. Then you're going to do what did you do and why did you give out your job someone else if you're going to retrain? But you are not starting from scratch because you do have a model that works on some distribution. You just don't have a model that works when you deviate the distribution. So can you retrain faster from using this model as a starting point, a clean model? And in some cases, you can show that's the case. So essentially, I'm going to finish is worst case adversary. So robustness, there's an obvious adversary there. He comes up with distributions where are different than what you trained on. We have this work on abstention with Adam and Yael, where we could show the rate of abstention on what you have been trained on plus the errors on what you are required to do inference on is bounded in the VC dimension, square VC dimension over n. There's work of one of your faculty members, actually, beyond worst case sequence prediction by Surbi-Goel and others, extending this to the online setting. And finally, I guess the elephant in the room here is that we haven't talked about LLMs. We've talked about predictive systems. And this is what everybody else is talking about. And there are lots of beautiful questions. So I think what's wonderful about this is a lot of questions that I think people that do have a theoretical background and do have a cryptographic thinking can make a difference. And for example, these are lots of questions about LLMs. You could see like the fourth bullet is about watermarking, and then there's copyright violation. There's some work on watermarking. First, Scott Aronson had a paper, then there was some group of people from Berkeley and Columbia, and Zamil that showed how to watermark outputs of an LLM. So you recognize it comes out of LLM. And then there's another paper by Boz and others who showed that that's impossible to watermark. So you can avoid all these methods. In terms of copyright, I think Boz has, and others have, have a definition on how would you avoid copyright claims. And that is that you would compare sort of training an LLM with a document versus training without a document and see the difference in these two LLMs. And if the difference isn't big, then you would say, well, I didn't violate copyright, obviously. But I think that the definitions from differential privacy, from cryptography are extremely useful in defining at least what you would want out of large language models. And I guess that's my last slide, and that is, I think that verification in data governance, so that I is a lonely I that should be part of an in, is very important. Sort of what data sources did you use? Did you tweak the data because you wanted to have certain outputs and not others? I think that's a very interesting space. Verification or verifiable AI, I think, is a very important area. By the way, verification versus computing under encryption is a much cheaper and much more doable task than the cases that we talked about, like the genome analysis or the DP genome analysis. And I said I was going to talk about legal stuff. I'm not going to talk about it, but there's going to be a conference on CS and law in Boston in March. And there's going to be a whole bunch of, the sessions are LLM for law, algorithmic fairness and privacy, AI and copyright, regulation of algorithms. So people interested in the legal setting, that's a good conference to go to. Thank you.
Thank you very much for that amazing talk. Thanks to our colleague, Professor Kern. We ran out of time for questions. No, but we do have time
outside
at the reception.
Okay, wonderful. Thank you.
Before that, I want to thank